everyone, and welcome to our lesson on geometric sequences. When we talk about a sequence, we're referring to a list of numbers that form some pattern. And today we're going to be talking about geometric sequences, which are lists of numbers that form a multiplication pattern. So not only does it have to be a multiplication pattern that you see to know that you're dealing with a geometric sequence, but it also has to be a constant multiplication pattern, meaning from one term to the next, to each other term, we have to see that it's been multiplied by the same amount each time. So we're going to be on the lookout for that kind of pattern. And when you see that that's the case, the amount that has been multiplied each time to get to the next term in the sequence, that's called the common ratio. So we're going to take a look at a few examples and identify the common ratio here. All right, so the first one here I see is 1, 3, 9, 27, 81. So you want to scan over from one term to the next and see if you can identify the number that is being multiplied to get to the next term. So 1 to 3, we know that's 3. 9, also 3. And if you follow along, you will see that each term is being multiplied by 3 to get to the next. So that's why this is a geometric sequence. It's the same common ratio all the way through. All right, second one on that examples list. I see a 5 and then a negative 10, and it goes back to positive 20, and then negative 40, and so on. It's alternating, so let's see what's happening. To get from 5 to negative 10, we would need a negative number, negative 2. Right, and then from negative 10 back to positive 20, you can see you will also need negative 2. We're talking about multiplying by negative 2. And it's going to continue happening. So we have a geometric sequence here where the common ratio happens to be a negative number, and that is fine. As long as it's the same all the way through, it's still a geometric sequence. All right, third one on the list here, we have 12, then down to 3, and then 3 fourths. It looks like it continues from there. So from 12 to 3, 3 is actually smaller than 12. So what could we be multiplying here to get to that next number? Looks like it's going to have to be a fraction. So from 12 down to 3, I'm going to need to multiply by 1/4. If I divide 12 by 4, I'm going to get 3. So it looks like 1/4 there. And then from 3 to get to 3/4 requires the same amount, 1/4. So the common ratio here, that would be from each term to the next, is 1/4. Each term's being multiplied by 1/4. All right, so on our other side, some non-examples. Let's see why they are not geometric sequences. So from 2 to 4, I could get there by multiplying by 2. But from 4 to 12, that would require a 3. 12 to 48 is 4, so it's changing each time. So you might be tempted to think it's a geometric sequence. It is a multiplication pattern. It's just not a constant pattern. So since we don't have the same common ratio each time, it is not a geometric sequence. All right, second one on this list. So 1 to 2 would require me multiplying by 2. To get from 2 to negative 4, same number, but it's going to be a negative 2. So even though it's the same number, since one difference was requiring a 2 and the other one was a negative 2, we can't say that it's a geometric sequence. And if you follow this along, it's going to continue to be inconsistent like that. Okay? So that is not an example of a geometric sequence. Okay, so we took a look at a few lists of geometric sequences. Now let's suppose that we are given a rule to follow to find a list for a sequence. Let's say that we are in charge of coming up with the terms for a geometric sequence following a certain rule. So how will we approach that? What we will do is the term that we're wanting to find, we're going to plug in that number for n. So this says find the first 4 terms of a sub n equals 6 times 2 to the n minus 1. So what I'm going to do, I want terms 1, 2, 3, and 4. So I'm going to plug in each of these numbers for n. So I want a sub 1 first. I'm going to use this rule, 6 times 2 to the 1, that's where my 1's going to go, minus 1. All right, so 6 times 2 to the 0, anything to the 0 power is 1. So 6 times 1 gives me 6. All right, a sub 2, and let's fill that out here. I'm going to need to plug in a 2 for n this time, so everything stays the same except for the number for n is changing. All right, 6 times 2 to the 2 minus 1. I've got to do this in the correct order. So I've got to do the power first. 6 times 2 to the first. So that's going to give me 12. Fill that in. A sub 3, and you can see the pattern here. Just any term you want, you're going to plug that number in for n. Let's finish this out. We want the third term now, so we're going to put a 3 in for n. Continue calculating that out. 4. And then the fourth term is 6 times 2 to the 4 minus 1 power. Make sure you do your powers first. Apply it to that 2, multiply by 6. Get a 48. So let's fill these last 2 in. All right, so these numbers here, we have just found the first 4 terms of this sequence. So if you want to check to make sure that you did this correctly, just something real quick you can do at the end is check to make sure the common ratio is constant from one term to the next. So to get from 6 to 12, that requires me multiplying by 2. Is that the same from 12 to 24? Yes. And 24 to 48. So looks like we're on the right track there. Okay, so let's suppose that we're in charge of developing a rule. We've seen lists that we have identified as geometric sequences. We've seen a rule given to us here where we had to find some terms. And now we're going to develop the rule from a list. All right, so if you take a look at the formula here, this is what you're going to want to use for a geometric sequence. A sub n equals a sub 1, represents your first term, times r, which represents that common ratio we talked about, the amount that's being multiplied each time, to the n minus 1 power, and n is the number of the term that we're talking about. So let's take a look at how we would do that. All right, so let's copy that down. A sub n equals a sub 1 times r to the n minus 1 power. Okay, so we can see that the pieces we're going to need are that common ratio and our first term. We can see the first term here in the sequence. We have that right off the bat. And then common ratio, we just need to identify the amount that is being multiplied to get from one term to the next. So 7 to negative 14, that requires me multiplying by negative 2. Let's see if it's the same from negative 14 to 28. Yes, I would have to multiply by another negative 2. So it looks like our common ratio is negative 2. So when I'm filling out and developing the rule, we'll have a sub n equals 7 times negative 2 to the n minus 1. We don't want to put in any number for n when we're writing a rule because a rule needs to still have a variable there so that we can use the rule to find any term we want. All right, so here's our rule right here. Easy as that. Okay, so let's put this to use. Let's use that rule that we just found to find, let's say, the 10th term of this geometric sequence. Okay, so let's copy it in. So we had a sub n equals 7 times negative 2 to the n minus 1. We would like the 10th term this time, so we're finding a sub 10. Okay, so all we have to do is put in a 10 for n. Make sure we follow the right order of operations. So let's do the 10 minus 1 first. Go ahead and put a 9 up there for the power. We're going to raise negative 2 to the 9th power. And we're going to have negative 512. So let's copy in what we have. 512. Then the last thing I'm going to have to do is multiply by 7. So the 10th term is negative 3,584. And we would not have wanted to sit and calculate this by hand all day, so it's very handy to develop a rule so that you can find any higher term that you might need. So this concludes our lesson on geometric sequences.